So let me now take this moment to introduce John Hauenstein, who is a professor and department chair at the Department of Applied and Computational Mathematics and Statistics at the University of Notre Dame. And John's been a faculty member there since 2014. And after earning his PhD in mathematics from the University of Notre Dame, he held various positions like at the Fields Institute, Texas A&M, Meetag-Leffler Institute, North Carolina State University, and the Simons Institute. So his research interests include numerical algebraic geometry and applications to nonlinear system of equations arising in sciences. So we're very happy to have him speak about this topic today in our seminar. So welcome, John, and take it away.
All right, thanks. So I want to thank Jose and the other organizers, Kathleen, for the invitation and allowing me to postpone off of your normal schedule. So thank you for that. And I hope to be able to see everyone in person at AG23. We had this virtual AG21. Be nice to get back in person for AG23. So today I want to talk about some applications of homotopy continuation in science and engineering, and kind of talk about some recent work that we've been doing here at Notre Dame. So start off with is just some quick introduction on parameters. So the whole idea about parameters is these are things that that the user can tune. So for example, if you're a chemist and you're in your chemistry lab, you can adjust the temperature on your Bunsen burner to be able to change the temperature of your water. By changing the temperature, you're changing the density. So you don't have a direct control on the density, but you can indirectly impact it by changing the temperature. So these parameters are things that we're able to control and adjust, and we want to see how does the system change as we change the parameters. Another example of parameters is when you're trying to synchronize coupled oscillators. So each one of these will oscillate around in a circle. And let's say they have uniform coupling, so we don't have to worry about that. The thing that we can control is how fast each one would rotate, so its natural frequency, if it wasn't coupled. So as these start spinning faster and faster, it becomes harder and harder to make this a coupled system that can synchronize. So the plot over here is a plot of these natural frequencies and the number of equilibria. So if the equilibria, or if the natural frequency is really small, so close to zero, then there's lots of different ways that it can synchronize. But as you start changing how fast these move around the circle, you get less and less ability to synchronize, and eventually there are no ways to synchronize the system. So what we want to do is we want to study how changing these parameters impact the system. And in this case, you see a nice plot of the number of equilibria as a function of the parameters. So today's talk is going to focus on the implicit function theorem and its relationship to homotopy continuation. So the implicit function theorem is what governs the relationship between the parameters and the variables. And homotopy continuation is just a special case of that. And then I'll talk about three applications in phase equilibrium, the maximum Gaussian curvature of a surface, and then some recent work that we've been doing with my current PhD student, Emma Kobian. She's in her third year. And then two other faculty members here at Notre Dame, Fang Liu and Daniel Shiavazi, on variational inference. So how we can apply homotopy continuation to statistical models. There. Okay, so the implicit function theorem is the main theorem that governs the whole ability to relate variables and parameters. So we have some system of equations F, and for simple sake, let's just assume they're continuously differentiable. Typically, these will be algebraic. So these will be nice polynomial systems. And so once you pick your parameters, then you have possible variables, solutions of the variables to the system of equations. So in this case, we have these two solution sheets over our parameter space. Once we pick a parameter, then we have these two solutions over them. The implicit function theorem tells you how these solutions change as I move my parameters. So the implicit function theorem is by Cauchy and Dini in the 19th century. It tells you that if you have these solution sheets, then you have a nice system of partial differential equations. So the partial differential equation tells you how the solution sheet changes with respect to each one of the parameters. The key part of this is you have this inverse Jacobian matrix here in order to set up this system of equations. So of course, it's only valid when the Jacobian is invertible. So at this point here, you have a singularity. The implicit function theorem would break down there. But generically on these solution sets, you have this system of differential equations that describe how the relationship of the variables and parameters. So let's look at a very simple example to illustrate. So the picture comes from the quadratic formula. So let's take it monic. So we only have two parameters, P1 and P2, as the coefficient of the linear and constant term. So the Jacobian with respect to x, take derivative as 2x plus P1. Derivative with respect to P1 is x, and P2 is just 1. And so the implicit function theorem tells us that if we have solutions to the system of equations, then those solutions has to satisfy this system of PDEs. So you get a really nice system of PDEs that describes how these solutions change. And in particular, since this is the quadratic equation, we know that the solution to this system of partial differential equations is given by the quadratic formula. So you can write down nice differential equations that describe how the solutions change as we move the parameters. And in some cases, you can actually write down explicit formulas, but we know that once the degree gets high enough, explicit formulas are not available. So what that means is we need to solve these differential equations numerically. And so to do this numerically, you use your system of differential equations as a predictor. So you can use your system of differential equations as a predictor to predict another point on this set. And then the nice thing about this system of differential equations is this describes level sets. So what that means is my function is constant everywhere on the solution to the system of differential equations. So wherever I start, that defines the level, and my function is always equal to that same level. So mathematically, this is what's called a first integral. So it's a function that remains constant on your system of partial differential equations. And so that gives us a way to do error correction. So the differential equations provide predictors, and then this first integral provides error corrections. So you can apply this to arbitrarily number of parameters and do predictor corrector tracking along these solution sets. And we've done this for multi-parameter SDPs, and it works out actually really well. So for those of us that have seen homotopy continuation, this should all look very familiar to you. And so let me explain that in more detail. So homotopy continuation is nothing more than applying the implicit function theorem where you have a single parameter. So we want to set up systems of equations that have this single parameter in them. So for example, if we want to solve a polynomial system, say 2 variables of degree 2, instead of solving that system, we solve an easier system. So here we can trivially write down the solutions. And then we set up one parameter that interpolates between those two systems. So our one parameter in this case is artificially introduced is a T, and it connects the solutions of my start system, which are easy to find, with the solutions of my target system, which is the one that we want to solve. So homotopy continuation is nothing more than a special case of the implicit function theorem, where we're over a single parameter. So if we have a single parameter, this Cauchy-Deany system of differential equations reduces down to a single equation, which goes by the name of the Davydenko differential equation. So it's the exact same system of equations when you have a single parameter. So this happens oftentimes in math. If someone reinvents something that has been identified 100 years earlier, and their name gets attached to it. So this Davydenko differential equation is nothing more than something that Cauchy and Deany discovered 100 years earlier in a much more general situation. So again, you have predictor methods. So this is an ODE, so you have an ODE predictor. And then because we have this first integral, because we know the function vanishes, we can correct back to the path. So homotopy continuation, you just have a single parameter where we have a path, but it applies much more broadly in the implicit function theorem where you have multiple parameters that you want to study. Okay, perfect. So as with the implicit function theorem, the Davydenko differential equation requires us to invert this Jacobian. So therefore, it's only valid when the Jacobian is full rank. But many problems, the interesting part that you want to compute are the critical points. You know, where are the critical parameters? That's exactly where the implicit function theorem breaks down because your Jacobian is rank deficient. So you want to push something to the limit. And when you push something to the limit, you have a rank deficient Jacobian. So the key aspect to do this is you want to describe a homotopy which ends at your system of interest. So for the sake of argument, let's say t equal to 0 is the ending point. We know that the implicit function theorem doesn't work at that point, but it works everywhere up to that point. So we have this open interval where it works up until the point where it fails. So what that means is we have well-defined paths which limit to these critical points. And then we can use endgames at the very end to be able to accurately compute those limit points. I don't want to say too much about endgames because it's not so relevant today's talk, but it's just based off of Poisson series expansions there. So you know that the Jacobian is rank deficient, so we can't, for example, use Newton's method locally, but we can use the fact that we have a Poisson series expansion to be able to accurately compute them. So what I want to do for the rest of the talk today is to give you several examples of how this has been used in various applications. And so the first one is in phase equilibrium. We'll see if the movie wants to work. There it goes. Okay. So here we want to study phase equilibrium of some object. And so, for example, water has a triple point. And so at this point, you have both liquid, solid, and vapor, and they exist in equilibrium. So here you see ice, water, as well as water vapor, all existing in equilibrium. So it's melting, boiling, and freezing all exactly at the same point in equilibrium. Okay, so ice is growing as well as melting, and bubbles are forming, which is the water vapor, all in this thermodynamic equilibrium. Okay, so we have all of these three phases existing at the same point. So this is very important in applications. It allows you to separate things. So in particular, the most often used in industry is the two-phase equilibrium. So where you can separate liquid and vapor from each other. Okay, so you put something in, you mix it, you get it to be in equilibrium, and then the gas will come off the top, the liquid will come off the bottom. So you can separate things in industry using this two-phase equilibrium. Mathematically, these are described by fundamental equations of state. And so these are highly accurate equations that describe this thermodynamic property. Okay, excellent. All right, so how does this work? Well, you get a system, you get two equations and two unknowns with one parameter. So you have this one parameter, which is the temperature. That's what you can control. So you can heat or cool depending upon your setup to get it to form an equilibrium. So your temperature is the knob you get to tune. The temperature will implicitly change the densities. So you have the density of the liquid phase and the density of the vapor phase. And what you want to do is you want to tune this so that the pressures are equal. So you have constant pressure and you have constant Gibbs free energy. So this is a system with two equations and two variables with one single parameter. So it looks innocent enough to be able to say, I want to apply applied algebraic geometry to this system. However, there's a lot of things lurking in the background. So the difficulty is that these expressions for pressure and Gibbs free energy are described by so-called Helmholtz free energy. You have the ideal gas law together with the residual piece, because things don't work in ideal situations in practice. And so this residual energy compensates for the failure of the ideal gas law. And this is where the main difficulty comes in, is because these are highly nonlinear. Everything that has an I here, that is some parameter that's come from data. So if you pick, say, carbon dioxide, it has a system of parameters that you plug in. If you pick another thing such as propane, then you get a different set of parameters here. So you see that you're going to have your variables here are tau and delta. So you're going to have some exponents. They're going to be real, but they may not be integers. You have the exponential function, again, not polynomial. You have some roots down here. So you have to take some roots maybe to a non-integer. And so the difficulty lies in this Helmholtz free energy. So it looks innocent enough until we start plugging in the expressions for the pressure and the free energy. But we still can apply homotopy continuation. As long as this is continuously differentiable, we can apply the implicit function theorem and homotopy continuation. So let's see how we do that. So we have this set of solutions. For example, for a given temperature, we have the density of the vapor, we have the density of the liquid that satisfy our system of equations. But we also have a lot of spurious solutions. Clearly, you see if these two densities are trivially equal, this system of equations just is identically zero. So you get this whole line of solutions just from the fact that you have these two sets of equations coming from this fiber over T. So you get all of these spurious solutions that you don't want to find. So you think about, say, saturating them out, but we can't do saturation because these are some very complicated nonlinear expressions. The other thing is that there's a critical temperature. So you can keep increasing the temperature until you no longer have an equilibrium. So there's this critical temperature. So this is the max temperature where you can actually maintain equilibrium. And at this point, you precisely have the densities are equal. So you're moving to this highly ill-conditioned, non-degenerate system of solutions here. So what that means is if you try to do, say, Newton's method, this is highly ill-conditioned and it's going to fail. So this is the problem in chemical engineering, is how to find the behavior near the critical temperature when things such as Newton's method fails. And so the idea is, let's use a homotopy. Okay, so we construct a homotopy which ends at this unknown temperature. Okay, we don't know what it is, so we treat T as a variable. And then we introduce a new parameter that forces these 2 points to merge together. So we're going to take these 2 points and merge them together. When these come together, they precisely come together at this critical temperature. So this is what's called a Newton homotopy, because the only thing that's changing is a constant. And that constant is, you can think of as the distance between these points. So we start off with some initial distance, and this homotopy brings those 2 points together. And it precisely ends at this critical temperature. Okay, so here's a plot of applying this to carbon dioxide. So we use the Span-Wagner fundamental equations of state, which are the commonly used ones for carbon dioxide. And each of these points is a point that, say, Bertini tracked along these curve in order to highly approximate the accurate critical temperature here. So the critical temperature is just over 300 Kelvin for carbon dioxide, where you have both liquid and vapor carbon dioxide existing in equilibrium. So you can find these solutions easily for low temperature. And then once you find them for low temperature, you can use a homotopy to track along them to force them to come together. Great. You can apply this to your favorite substance: methane, ethane, propane, oxygen, nitrogen. And we pulled equations out of the literature. We ran this homotopy, and all of our critical temperature, pressure, and densities agreed with the common literature in chemical engineering. Not only are we able to find these critical temperatures and pressures and densities, but we also are able to build a local model nearby. And so you can accurately compute values near the critical temperature. So down here, when the temperature is low, it's easy to compute, but now we're able to compute locally near the critical temperature as well. So this gives the engineers added information. Okay,
hey, John, before
yes,
you
please
go on, Alicia Dickenstein has a question. Do they need to know beforehand that there is a unique maximum?
So in this case, it's known that there is a unique maximum, and these things have to come together at that point. If you don't have a unique maximum, then you could be tracking along one curve and then another curve, and those 2 curves don't actually come together. And so that's a great segue into what I wanted to talk about next. So thank you, Alicia, for the question. So if you have multiple maxima, you could have multiple points and you don't know which ones actually come together to form that maximum. And so if you can't force them to come together, you're going to run into problems. So in particular, let's say I only have one point. I don't know its friend that's going to meet the maximum. How can I use that one point to go to the maximum? Okay, and we'll apply this to compute the maximum Gaussian curvature of a surface. Okay, so if you, in that experiment here with chemical equilibria, we know that there's a liquid and a vapor phase, and those have to come together. But in other problems, you don't know. And so how are we able to compute the maximum in those cases? Okay, so let's describe the setup. So you start with some domain over the real numbers, and you're given some boundary function G. You want to describe a surface by a function over that. So you look at the graph of a function over your domain. So that's a surface. And now you want to find the surfaces which have a constant Gaussian curvature. So they have a constant Gaussian curvature K if they satisfy this system of equations. And you see that you have this boundary function G on the boundary of your domain. So given a domain and a boundary function, find a surface with a constant Gaussian curvature. So you have to solve this system of differential equations. There exists a maximum that's possible. This maximum depends upon the domain and the boundary function. And so you want to find the largest one that exists. The problem is we can't actually force two things to come together because this system, as a system of PDEs, only has a unique solution if a solution exists. So you can't actually force things to come together like we did in the last one. So what do? You don't know where the maximum is. So what do? Well, there is a paper from roughly 25 years ago that says, well, let's take a sweeping approach. So start somewhere and then just kind of increment along the way and keep incrementing until the solution disappears. And so this leads to many questions, such as how fast should I increment along until I hopefully run into this maximum? And then this is a system of PDEs. How do I know that the solution actually disappeared? Maybe I just didn't set up my PDE solver correctly. And so the sweeping approach has many challenges. So you see here, going back to Alicia's question, we don't have another one that we can force together to end at this point. So all we have is a single point, and we want to push it to the maximum. And so what we want to do is we want to construct a homotopy that ends at this unknown K max. And the way you set this up is you look at where does the Jacobian drop rank. And a nice numerical description of where a Jacobian drops rank is on the minimum singular value. So if you have a single point, what you do is you push the minimum singular value to 0, and that'll end at this maximum. Okay, so here's the form of it. So you have your system of equations coming from your PDE, and then you set up a homotopy which forces the minimum singular value to go to 0. And so you start with one point, and it moves to the critical point based on this minimum singular value. So we don't have to have a second one that converges. This is all just local on that path. Great. So we applied this to a problem from this Baginski-Whittaker paper. So they took this square domain. I'm not quite sure why they used 0.57, but that's what they did. And then they had this boundary function coming from the square root of 1 minus x squared minus y squared. So we want to compute what is the maximum constant Gaussian curvature on this domain with this boundary. And so, for example, when you have low constant curvature, say 1, it's really easy to find. So you can find a solution easily. And now what you do is you push K larger by making the minimum singular value go to 0. So we're increasing K by forcing the minimum singular value to decrease. And based on your discretization, you get slightly different values of this maximum curvature, but it's just over 2. So this is a 2-dimensional, so this is 32 grid points in each of the dimensions. Excellent. So you're able to push to a critical point from just knowing one point. You don't have to know where the friend matches up. Okay, so to summarize, we use 2 different kinds of homotopies here. The first one with this constant Gaussian curvature was uniform in this minimum singular value. So the t uniformly decreased this minimum singular value. In the problem when we were studying chemical engineering, the t uniformly decreased the distance between these densities. So we get some kind of way to describe how these homotopies work. Uniform in some measure that makes it easy to see. So this SVD homotopy, which is joint work with Jeb Collins that just got published earlier this year, is much more applicable because you don't have to have other things to force together. So this SVD homotopy works in many more cases than this one that forces things to come together. Okay, so now let me end with my last example, which is related to probability and statistics, is how can we use homotopy continuation to sample points given a complicated probability density. Okay, so you have some complicated probability density, and now you want to know, how can I sample points from this density? That's a hard problem. And so what people have proposed is they start with something easy, say a Gaussian distribution, and then they come up with a function that transformed this Gaussian, which was easy to sample, into this complicated one. So you transform from something easy to your complicated expression. And so you set the possible maps that you want to consider, and you try to find the best one. So you want to compute the critical points over this set of maps. Let me describe some mathematics behind this, but that sort of gives you a quick overview of what we're trying to do. So what does best mean in this case? Best means in terms of the KL divergence. Okay, so the KL divergence is this famous formula from the 1950s to be able to measure the difference between 2 probability distributions. So you have 2 probability distributions, P and Q. They're given by densities, little p and little q. And this is the KL divergence. You just take the integral of this expression. It's not a metric, but it has a lot of nice properties. For example, this is always non-negative. So this KL divergence is always non-negative, and it's 0 if and only if you're exactly the same distribution. So minimizing this function, this KL divergence, tells you a lot about how accurate you can compute this probability distribution. So the goal is to minimize the KL divergence over some family of maps. And in the world of AI machine learning, the nice type of maps that people consider is compositions of easily described maps. So for example, k-planar flows, you take a composition of k functions where each one has a very simple expression. So you have these parameters u, w, and b, and they just describe how do I change. I do a linear transformation. I apply an activation function, such as ReLU or hyperbolic tangent, and then I scale it by this parameter u. Okay, so these are the common types of maps between distributions that people consider. And you can take K to be like 100, 200, 1,000. So you get more and more complicated as you compose more and more functions together. So this is all great, sets up nicely until you actually try it in practice. And what happens is, as you do this in practice, you get lots and lots of minima that are actually pretty terrible. So for example, if our target distribution is a simple bimodal distribution, when we apply this minimization, we end up at many of these bad local minima, where you only capture, say, one of the peaks. So it's great in theory until you actually apply it in practice, and you end up with all these bad local minima that you don't want to find. And so the paper that described this, Resende and Mohammed paper from about 6 years ago, in the example section, they have this one sentence that says a simple annealed version is used because this was found to provide better results. So they didn't talk about all of these bad local minimas and all the problems. They just said, oh yeah, by the way, we have to use an annealed version because what we described didn't actually work as we wanted it to. Okay, so let me try to unpack what this means. What they're doing is they're taking their density function Q and they're raising it to a power T, where T goes between 0 and 1. So when T is equal to 1, that's our target distribution. And then as T goes to 0, it becomes more and more constant and easier to find, easier to describe. So what they're doing is they're doing a homotopy over density functions. So they're doing a homotopy over density functions in order to do this variational inference, in order to be able to sample from these complicated distributions. Okay, so here's an animation of how it works. Okay, so I'll restart that animation. So you start with something much easier, and then it continuously deforms into your target distribution, and it makes it much easier to optimize over. And so you can find that multimodal distribution much easier when you use this homotopy approach. Okay, perfect. So Resende and Mohammed took uniform steps in T. The problem is the distribution doesn't change uniformly. So our goal was, can we rephrase this in terms of a homotopy and make an adaptive approach which is uniform in this KL divergence? So if you see here, my pictures are not uniform in T. These are based on exponentials, which are not uniform. And so taking a uniform step size in T is not a good approach. And so here's the theorem. If we treat this as we're going to take steps along a homotopy. So we want to step from T to T plus delta T. How much does our distribution change? Well, it's based on the square of delta T times the variance, plus some higher order terms. So if we want to do a homotopy, which is uniform in the KL divergence, then what we do is we take our step size to be inversely proportional to the standard deviation. So we don't want uniform in T, we want uniform with respect to KL divergence, which means we want them based on the standard deviation. And the nice thing about this is we can actually approximate this locally from known data. So it makes it really easy. So uniform step size in T is terrible because the KL divergence changes not uniformly. We want to take a modified approach based on local behavior of the standard deviation, so then we can have a uniform across the path. Okay, So I'm running out of time, so I'll just end with some plots and an example. So the Resende Mohammed took a constant in T. That's not the right approach. You want to do adaptive tracking. It starts off smaller step sizes, and then as T gets closer to 1, then you can take much bigger step sizes. So let me end with a very simple example from biology. So you have this HIV model. So it's a system of 3 differential equations, and there's some parameters in there. To visualize it, we wanted only 3 unknown parameters. So we fixed some of them and we left 3 unknown. If you have exact data, so if you're able to have exact output data, then there are 2 sets of parameters that can describe that output data. So this is what's called the identifiability degree. How many parameters can describe exact data? And in this case, there's 2. But now, as soon as you throw error in there, those 2 points now become distributions locally. So you get this multimodal distribution centered at those 2 exact values. And the most important thing of this is the plot here. You see that T has to stay really, really small for many steps in this homotopy because the distribution is changing really fast. So the distribution is changing really fast. And so if we want uniform in this change, we have to take T really small. And then as soon as we start getting closer and closer, then we can take T much faster. So along this path, we have a uniform in the KL divergence. So let me just wrap up. So when you're looking for critical points, you want to formulate your homotopies to end at the system of interest, because now you can apply endgames to accurately compute things. Anytime you set up a homotopy, you want to think about, how does my parameter T impact how things are changing? So it would be nice to have your parameter T uniform in some physically meaningful quantity. And for here in this variational inference approach, the quantity of interest is the KL divergence. So we set it up to be uniform in the KL divergence. And what this shows is you get a robust and efficient way to find these multimodal distributions. You get rid of these bad local minima that appear, and you find the global minimum in a robust way. So I'm out of time, so I want to thank everyone for coming, and happy to answer any questions.
Fantastic. Thank you, John, for the talk. And so if people have questions, please post them in the Q&A or in the chat. One question to get things started is from Carlos Amendola, who asks if you could comment more about the technique. Are you sampled directly from the easy distribution and then tracking the sample points as you deform to the target distribution, or could you say a little bit more?
Yeah, that's right. That's right. Okay, so perfect. So you start off with a distribution like this. Let's say we still don't know how to sample from this distribution, but it's much easier to use optimization to approximate this distribution. So you start off with something which is easier to approximate, and then you sample from the approximation to it. Okay, so where did that? Yeah, perfect. So as it starts off, you have some distribution you don't know how to sample from, but it's much easier to approximate. And so when you're doing the optimization, you still don't know how to sample from it, but you can approximate it much easier. And then as T increases, the key thing here is the support of this. the support of this. So you need to find samples inside of each of these peaks. That's essentially what the method boils down to. You need sample points in each side of these peaks. As t goes to 0, things, go to the constant function. And so you're increasing the support of it. And so you can get lots of sample points in here with your approximation, and then let t go to 1, do a homotopy as t goes to 1. It's uniform in the KL divergence. And so it changes uniformly as we restrict back to 1.
Thank you.
Oh, go ahead.
Another question from Charles Wampler. In the SVD homotopy, are you numerically differentiating the minimum singular value to track it?
Yeah, that's right. So what I did not, I wrote the homotopy in this way for ease of presentation. But what you actually do is every singular value comes with a left singular vector and a right singular vector. You use those left and right singular vectors to be able to actually do this homotopy. So you need a way to describe what does it mean to be a singular value, and you use the left and right singular vectors to be able to do this, and that gives you a way to differentiate the minimum singular value, is by studying how the left and right singular vectors change.